All right, let's continue with the talk by David Wallace, who will be talking about interpreting the quantum mechanics of cosmology. Please, David.
Thank you. As Chris just pointed out, it's not May 22nd, so don't adjust your watches. So I want to come at the question here a little bit indirectly. I'm going to start by talking about the quantum measurement problem a bit and kind of creep up on cosmology sideways. So here's my starting point. There's a fairly commonly advocated thesis in philosophy of quantum mechanics that you might call the quantum underdetermination thesis, which basically makes the quantum measurement problem a sort of quintessentially philosophical problem, a problem that can be engaged with in a way that's largely disconnected from the practice of physics. So there's sort of two parts of the underdetermination thesis. The first is something like, well, if we're deciding should we be, quote, realists about quantum mechanics or, quote, anti-realists, that's a question to be decided on sort of broadly philosophical a priori grounds. So if you're asking, for instance, why should our theory describe objective reality, the answer will be some philosophical answer along the lines of, well, that's what science is supposed to do. Or if we're asking, why shouldn't measurement play a primitive role in our theory, it's going to be something like, well, we want our theories to tell us what measurement devices are. We want our theories to be reductionist in some sense. We don't want these sort of primitives in our theory. And the second half of the thesis is, once you've established a class of realist interpretations of quantum mechanics, we've got the classic philosophy of science issue of underdetermination of theory by data. So in other words, we have a class of interpretations of quantum mechanics, and the classic way this is stated in the literature would be something like dynamical collapse theories versus Bohm-style hidden variable theories versus Everett many worlds type theories. Once you've got these multiple realist interpretations of quantum mechanics, they're all compatible with the data. We can understand quantum practice equally well with all of them. So our commitment to one interpretation or another turns on extra empirical matters about, ontological extravagance or fit to the manifest image or preservation of determinism or what have you. And so arguably at least that floats free of anything that's going to come out of scientific practice. That's been a theme in philosophy of quantum mechanics for a very long time, but it seems to have become more prevalent in recent years. So, Craig Callender advocating this about 5 years ago, Matthias Egg a little later than that. Here's a very recent paper taking this as a starting point to argue against scientific realism. And I think one of the reasons this is kind of in the literature is a sort of feeling that the debate about, the sort of philosophical debate about the interpretation of quantum mechanics has sort of reached a bit of an impasse in the last 5 to 10 years of the literature. I've been kind of fighting a small campaign against the quantum underdetermination thesis for a while. There's a couple of papers of mine objecting to it in various ways. And in some ways, this talk is going to be another step in that objection. Why is it relevant here? Well, what I want to say is that the class of sort of, quote, interpretations of quantum mechanics actually kind of involved commitment on various different ways to do physics. And for that reason, there isn't anything like that kind of separation of the interpretation of quantum mechanics from how we use quantum mechanics, how we do quantum mechanics as practicing scientists. And there'll be an ecumenical version of that, which is that I think one thing that shows is that the debates about the interpretation of quantum mechanics have had and continue to have more relevance to the practice of physics than some people in physics have tended to think. And there'll be a non-ecumenical version of it, which is that the way to interpret quantum mechanics that I prefer is correct. We can take the first bit on board and reject the second bit. I won't hold it against you. Here's how I actually want to structure that. I want to say that there's, broadly speaking, and any classification scheme simplifies, and as I was saying in comments to Charlotte's talk, every classification scheme builds in ulterior motives, so there are almost certainly ulterior motives here. So I want to say there's broadly 3 ways of doing quantum mechanics as science that come out of the measurement problem debate. And I'd call those, apologies for the slightly zen way of describing this, the way of modification, the way of the lab, and the way of decoherence. And basically what I want to argue is that, well, firstly, I'd say that we've got substantial insights into quantum theory from all of these ways of doing quantum theory, but, and this is the more contentious claim, that it's only really the way of decoherence that's successful in making sense of a large part of the practice of quantum mechanics as we actually do it at the moment, and a particular relevance to this conference of how we do it in cosmology. Okay, so I'm only going to talk about the way of modification briefly. The way of modification basically says quantum mechanics, for all that we can kind of concoct and distort and twist it to get data out, is fundamentally broken as a theory of physics, and so the only way to get physics back on some conceptually clear foundation is to change quantum mechanics, to modify the equations or to supplement them with other things. The classic descriptors of these are something like the GOW and continuous state localization, dynamical collapse theories, and the various hidden variable theories coming out of De Broglie and Bohm's work, various forms of the modal interpretation, various retrocausal strategies arguably fall in the same space. In support of the sort of ecumenical commentary I was going to make, I think it's obvious when you put it that way that we've learned a lot about the structure and nature of quantum mechanics through thinking about the way of modification. The Bell inequalities are the most obvious, but by no means the only example of this. The way of modification at present doesn't give us a way to do currently observationally relevant quantum cosmology. And what I mean by that is if you look at the way early universe quantum mechanics is used, we're basically using the following kind of ingredients. When we're looking at the kind of pre-recombination era, we're largely doing effective field theory. We're using the various tools of quantum field theory to study nuclear synthesis, to study the quark to hadron phase transition, to study the electroweak symmetry restoration. When we're looking at structure formation, we're using what I've called elsewhere low energy quantum gravity, which is effectively effective field theory when we include general relativity as one of the components in the effective field theory story. It's a non-renormalizable theory. It breaks down at high energies, but that's not a problem in effective quantum field theory. Salient to Charlotte's talk, if we want to do very early universe quantum mechanics, then we need ultraviolet quantum gravity theories, theories like loop quantum cosmology, theories like string theory, pick your favorite strategy. I'm actually going to be less concerned with those kind of strategies in this talk. What I want to talk about more is those places where we're using quantum mechanics to make testable predictions in contemporary cosmology. So the kind of what I think you call the quantum gravity wall in your talk, that's a place where our developments are quite theory-driven and where we're only at the embryonic stage of making concrete predictions. But of course we make a lot of concrete predictions in the somewhat later periods of the early universe. Those predictions lean heavily on quantum mechanics. Many of those predictions are extensively tested. Others of those predictions are accessible to testing in a way that isn't yet possible for the sort of pre-quantum wall physics. And the point about these approaches is they're kind of using the full panoply of effective field theory in sort of complicated regimes involving symmetry breaking, finite density, finite temperature. These are not at present things where we know how, in the way of modification, to modify quantum mechanics and reproduce all of the panoply of empirical evidence supporting those approaches. So the classic success space for the way of modification has been non-relativistic particle mechanics. There have been interesting extensions of the theory into various bits of the relativistic regime, some of them by people in this room. But I think everyone would agree that we're not yet at the stage of having modificatory approaches that reproduce the full panoply of renormalized, symmetry broken, finite density, finite temperature, standard model physics. Whether or not we'll be there at some point is an open question. It's, to me, overwhelmingly the most important question in the way of modification, far more important than the philosophical questions of interpreting those theories. But right at the minute, if we want to make sense of the cosmology we're actually doing, the way of modification isn't an option. It's a route to try to find, to try to sort of take an end run around the limitations of that, but it's not something that can be used to make sense of the physics that's currently being done. Oh, I should say, this is an example of how it sort of gets even more complicated. You bring in GR, things like the sort of GR as an effective field theory, as a path integral definer. Again, last time I looked, well outside the space of us having way of modification reproductions of it. And it might be said, incidentally, that if one's an advocate of the way of modification, one wouldn't necessarily want to be simply reproducing passively the results of extant physics, but actually hoping to go beyond that. That's something I'll come back to briefly at the end of the talk. Okay, let me talk about the way of the lab. The way of the lab is something that undergraduate quantum mechanics textbooks arguably tend to commit to. The way of the lab says something like this. Any application of quantum theory is relative to some fixed experimental setup. And the way that works is a kind of three-part process. Again, I'm leaning, I think it's my kids are watching Kung Fu Panda at the moment, leaning heavily into this kind of, three ways and then the ways of the ways. The three steps we have of the way of the lab, there's the preparation of the state, which is a primitive thing to be understood outside quantum mechanics. There's the dynamics of the state, where it evolves in time, that is to be understood quantum mechanically. And then there's the measurement of the state, which is again a primitive thing lying outside quantum mechanics. Should I be concerned about the... I think the computer is just sort of commenting when it particularly likes or dislikes something I say.
Maybe it's emails.
If you've got an email browser,
yeah.
It might be the reason.
I think that was the reason, unfortunately. I'm sorry.
It's no problem. And a corollary of the way of the lab is, insofar as classical mechanics tend to be used as the language in which we describe the machinery that does the preparation and measurement and which is not to be understood quantum mechanically, then the transition from the quantum to the classical is normally seen here as a conceptual matter and not simply something to be understood dynamically. And this speaks to some of the discussion we were having after Charlotte's talk. So, examples of sort of interpretations of quantum theory that I think are broadly along the lines of the way of the lab. Straightforward operationalism of the kind that Heisenberg or Asher Perez liked. Bohrian complementarity has pretty much something of the same flavour. The cubist strategies and their various descendants and ancestors have that character. Healy's pragmatism has that character. Arguably, you could say measurement-induced collapse of the wave function has that character. There's a sense in which you might call that the way of modification, but the way in which measurement-induced collapse tends to get used is something like you're not supposed to, contrary to the dynamical collapse strategies, you're not supposed to ask silly questions about exactly when the collapse happens, or why it happens, or what the mechanism of it happening is. It happens when we measure things, shut up and calculate. So there's a sense in which I think actually, even though in a sense it modifies the equations, measurement-induced collapse is again a way of the lab approach. The way of the lab, incidentally, I'd say is more or less the default assumption in quantum information. And again, it's been extremely effective. The austerity of this description of quantum mechanics has been highly informative in developing the various ideas of quantum computation and quantum information, which get their power from abstracting away a lot of the messy detail. However, the way of the lab claim is insufficient for a large fraction of actual physics practice. I think without some finessing, it's not even suitable for a full description of what happens in the lab. Why do I say that? Well, firstly, measurement devices aren't primitive. We don't actually head out into the desert and find measurement devices dropped off by alien races with a sort of stamp on them saying, I measure this observable. We actually build these things. I'm not an experimentalist, but I'm reliably informed that we build measurement devices out of atoms and that we build them according to known physical principles. So we need to understand and model those physical principles. And of course, while it was okay for Bohr to model those things classically, and that's a key aspect of understanding the Copenhagen interpretation, modern quantum measurement processes are themselves heavily quantum mechanical. We also have trouble, I'll talk only very briefly about these points on time grounds, we also have serious trouble understanding the notion of repeated measurements in the way of the lab. Something like the quantum Zeno effect is an illustration of this. We have serious problems understanding something like continuous observation in the way of the lab. It's noticeable that Schrödinger's original thought experiment didn't involve a discrete quantum measurement as it's normally set up in the foundations literature. It involved putting the cat in a box with a radioisotope and waiting until the appropriate half-life length had passed for there to be a 50% chance of decay. But the appropriate quantum state there is some superposition of the cat dying at all the various instants of time. The formalism of measurement has generalized in the last 30 years to cover positive operator value measurements that, again, don't fit well in the way of the lab. And there's a general move that's been made in the quantum mechanical modeling of measurement in response to these kind of concerns, which gets called the church of the larger Hilbert space. I once at one point described as the Church of England version of the Everett interpretation, for anyone sort of familiar with British institutions. So the Church of the larger Hilbert space is the observation that in practice, the way we handle these limitations, the way of the lab, is we step outward. We extend the quantum framework, expand the quantum framework, so the measurement device is still a quantum system, but we at least pay lip service to the idea there's still an external measurement and preparation process over and above that. So you always have to have a quantum classical split or a quantum observer split or what have you, but you can move that split so as to incorporate the measurement device if you want to do some physics on it. And that requires that boundary between quantum system and external preparation and measurement to be something that can be moved. And you can see this in the classic and more recent literature. Von Neumann's early talk of a cut absolutely has this in it. Von Neumann talks about the ability to move the quantum classical split so as to include or exclude various bits of the measurement process in the quantum formalism. Something like the relationist approaches that Carlo Rovelli and co-workers have developed have something of this character. We always have to have a quantum system being understood in relation to other systems, but we can always incorporate more systems inside our system if we want to, provided there's still a system outside it. So the way of the lab already has to be complicated quite a lot to handle the lab, but I want to suggest that this is really just a special case of a more serious problem for the whole approach. And this is where we'll loop back to cosmology. When we go into the wild, outside the lab, we'll find many areas of study in physics where we have ongoing, objectively treated historical processes, or processes in general, that make essential use of quantum mechanics. I mean, there are silly examples just in the room. If I want to say, why is this cold? Then I want to say something about, well, it's about the low heat capacity and high thermal conductivity of metal. Why does metal have have those features? Answer, because of how the delocalized electron bands work. How do we understand the details of that? Quantum mechanics. How do we throw that kind of just description of the actual properties of a thing into the way of the lab? Don't look at me. But there are more dramatic examples that I think make the point more forcefully. So here's one. Think about solar astrophysics. Quantum mechanics is essential to solar astrophysics. We have our various models of what's going on inside the sun. Quantum mechanics is playing an important role in those models. Those models let us say things about how much energy is generated in the sun and how that has changed over time. They let us predict that the sun is hotter now than it was hundreds of millions of years ago. We can plug this kind of thing into paleoclimate data, and we can relate it to various bits of geophysics on Earth. We can have it as a data point in historical models, and to some extent we can look at the feedback of those historical models as part of our confirmation story for the whole framework. But it's Procrustean, I think, to say that a least squares best fit to a paleoclimate model counts as a quantum measurement of the nuclear fusion processes inside the sun. Here's a slightly more morbid example. Nuclear weapons make essential use of quantum mechanics. The radioisotope generation in mid-century nuclear tests shows up in increased levels of cancer. Quantum mechanics is intimately caught up in that story, but again, I don't think we want to say that higher incidence of cancer count as a measurement, a quantum measurement of the nuclear processes in the Bikini Atoll nuclear tests. And the third, and of course most salient example for this meeting, of course, is structure formation in early universe cosmology. So our stories about structure formation in the early universe essentially advert to quantum fluctuations as a source of the anisotropy. The most worked through and most widely studied model of that is inflation. I'm going to talk in terms of inflation. I think the claims I'm making will largely go through mutatis mutandis if you have other preferred quantum theories of structure formation. The way we do inflation calculations of structure formation goes something like this. We treat the inflaton field coupled to the metric field as a quantum field. We have a quantum gravity theory here. Notice it's, the inflaton field is in a superposition of different states, so the metric is in a superposition of different states. We evolve that inflaton field forward unitarily through the periods of where inflation rolls out. After a certain point, we start treating the mod squared amplitudes of the fluctuation modes as if they were probabilities. And then we hand those probabilities over to colleagues who are working in structure formation. So there's a sort of division of labour. There's a quantum mechanical calculation that generates a probability distribution, generates a mod squared amplitude distribution over different anisotropies. There's an interpretation move where one reads that mod squared amplitude distribution as a probability distribution, and then there's a handing of that stuff over to people who, for instance, do the sort of calculations to see what that translates to for the cosmic microwave background radiation that things like the WMAP satellite observe, or the much more involved calculations that tell us how that leads to the observed distribution of galaxies and galaxy clusters that we see in the night sky. So it's a very involved, model-dependent, but also very quantum mechanical requiring story. And it's worth saying, and I think this is why I want to focus on this early but not quite so early universe cosmology, these are cases where theories are making testable predictions. You know, the inflation theory of structure formation, for instance, makes claims about the spectrum of distributions in the WMAP data. They're not desperately precise claims, but they're not trivial either. Those claims fit the data. This is salient to the support of inflation. One of the challenges for non-inflationary descriptions of the early universe is to have a comparable story to tell about structure formation. What are we doing in that story? We're effectively reading certain features of the quantum state probabilistically. We're not plugging ourselves into a formal quantum measurement process. We're not saying something about what would happen if we did a quantum measurement. We're just directly saying we've got a mod squared amplitude distribution over certain degrees of freedom, and we're just treating that now as a probability. In very much the same way as we treat a StatMech probability distribution. And there's a whole other set of questions about just how objective that is, but bracket that for the moment. Now, of course, that's not a consistent interpretation of quantum mechanics all the way down. We can't consistently understand mod squared amplitudes as probabilities for straight off for everything in quantum mechanics, because we run into, well, the measurement problem ultimately, and we run into interference effects, we run into the kind of things that are ruled out by a panoply of no-go theorems. So we know that it's not a systematically consistent interpretation of quantum mechanics to say mod squared amplitudes just are possessed probabilities. Notice that the way of the lab dodges this by saying mod squared amplitudes of measured quantities are possessed properties, which is why, because I'm only actually measuring one thing in the way of the lab, then my measurement process itself determines what things get probabilities. I'm saying that in the application of quantum mechanics we're using in these various historical processes, including early universe structure formation, there's no measurement context brought in. We're just straight up saying some degree of freedom is such that we treat the mod squared amplitudes for that degree of freedom as probabilities. We can't do that all the time. At a fundamental level, we can't understand quantum mechanics as being about probabilities, it's about amplitudes. But mostly when we apply quantum mechanics, we're not working at a fundamental level. What we're doing is we're identifying some smaller, coarse-grained set of degrees of freedom, and we're interpreting the mod squared amplitude over those degrees of freedom as a probability. And that brings us on to the way of decoherence. The way of the decoherence says that the way we extract empirical content from our physical theories, our quantum theories in particular, is we look for approximately autonomous equations for certain higher level degrees of freedom in regimes where those equations are deterministic or stochastic, but not quantum mechanical, not interferency. These are decoherent regimes. They're regimes in which these degrees of freedom, formally speaking, obey classical deterministic or stochastic dynamics. Then we're interpreting those dynamics realistically, which is to say we're saying, yeah, we'll regard those equations as actually being the equations of things which evolve deterministically or stochastically and have possessed values. And as a special case of this, the quantum classical transition, or really in some ways just the entirety of this, the quantum classical transition is this kind of thing, and so is a purely dynamical process. So the way of decoherence just says, I've got my big complicated quantum system, it's evolving unitarily under the Hamiltonian, observers don't get a look in, but in that system I identify coarse-grained or collective or otherwise autonomous degrees of freedom that obey quasi-classical equations, and then I just read content off those probabilistically. So for instance, the macroscopic degrees of freedom of measurement devices abstract over the device's microscopic details. The bulk thermal properties of the core of the Sun abstract over the vast number of compatible microstates that make up the core of the Sun. And in inflationary cosmology, the low wavelength modes of the inflaton field, which are the things that give rise to the primordial inhomogeneities, are got by abstracting over the high wavelength degrees of freedom and the other fields present. So we can consider the low wavelength degrees of freedom as a small subset of the degrees of freedom of a system that also includes all the fields that aren't the inflaton field and all the modes of the inflaton field that are at shorter wavelengths than the ones we care about. Now, all of that relies on the fact that it actually is true that those degrees of freedom are autonomous, that obey autonomous equations. But we know quite a lot about why that happens. Sometimes it happens because we have isolation. Sometimes it's just because those degrees of freedom don't couple at all to the other degrees of freedom. The centre of mass of a planetary body is an example of this. For broadly symmetry reasons, the motion of the centre of mass is largely just dynamically decoupled from the behaviour of the other degrees of freedom. This is normally not a stable source of dynamical autonomy because some other system can come along and measure it and interact with it and break the disconnection. More commonly, we have something like a statistical autonomy. There are lots of degrees of freedom, vast numbers of degrees of freedom interacting with the degree of freedom we're interested in, so many that we can average over them, and in doing so, more or less take advantage of the fact that the thermodynamic equilibration timescale of those degrees of freedom is fast compared to the dynamical timescales of our coarse-grained degrees of freedom. And that gives rise to dynamics that are autonomous, but decoherent and time irreversible. It's helpful, by the way, here to distinguish between two ways in which those microscopic, fast equilibrating, numerous degrees of freedom can be present. So the most common one sees in explications of decoherence theory is environment-induced decoherence, is the idea I've got a different system's degrees of freedom. So here you might imagine that the inflaton field is decohered by gravitons or by the electromagnetic field or something. So in quantum mechanical terms, we'll trace over the electromagnetic field or the graviton degrees of freedom and get out some decoherent dynamics for the inflaton field alone. But alternatively, I think actually in many ways this is often the more important process conceptually. Decoherence happens from a system's own small-scale degrees of freedom in the way in which the large-scale modes of a system can be decohered by the short wavelength modes of the system. So if I tap the table, quantum mechanically, I'm generating pulses of phonons that move through the table. all of that's quantum mechanical. Why can I effectively treat sound waves in the table as classical? Well, answer, the relevant sound waves are long wavelength modes. Those are being decohered both by other stuff that's out there and because the table is not fully harmonic, so there's coupling between the long wavelength modes and the shorter wavelength modes, and my big bath of thermal modes is itself enough to decohere the sound waves. So in any case, applying the way of decoherence, we have these numerous and relatively well understood physically mechanisms by which we in fact get the kind of autonomy of collective degrees of freedom that means they're evolving according to deterministic or stochastic, formally speaking, evolving according to deterministic or stochastic equations. Formally speaking, all the way here, I haven't said anything about why that's justified. So, claim, the way of decoherence, that way of doing physics, is the way in which physics is actually being done in the kind of contexts that are salient to what I'm calling early universe cosmology, so distinguished from super-duper early universe cosmology, which was what Charlotte was talking about. And so we then want to ask, okay, well, what ways of interpreting quantum mechanics are there that are compatible with the way of decoherence, that make the way of decoherence the right way to do physics? And, of course, the Everett interpretation is the classic example of that. In fact, the way I would understand the Everett interpretation can be understood as an attempt to interpret quantum mechanics compatibly with the way of decoherence. It's a standard line in philosophy of physics that that decoherence doesn't solve the measurement problem. Philosophers or physicists, a way of seeing how confused physicists are is how many physicists say decoherence solves the measurement problem. If you like, the sort of emollient way of understanding the Everett interpretation is what's a way of understanding quantum mechanics such that it's true that decoherence solves the measurement problem. And the Everett interpretation is very much an attempt along those lines. Specifically, in the Everett interpretation, we're taking the quantum physics as describing some isolated systems that are not conceptually requiring any observation or external system to interpret them. Because of interference, we can't interpret quantum mechanical states and dynamics as fundamentally probabilistic, but we can get content out of the theory via the regimes in which we can emergently interpret it as probabilistic. And we learn about those regimes by studying the dynamics of the full theory, disconnected from any measurement contexts, and so we need to take the full theory's dynamics seriously. And in particular, measurement is only a special case of high-level dynamics, starting with an initial magnifying up of microscopic superpositions to a macroscopic scale and then proceeding from there. And then the Everett interpretation, I'm not defending here at all that it can do these things. What the Everett interpretation needs to give you is a philosophically coherent justification of how we can understand the theory as fundamentally not probabilistic, but emergently probabilistic. And the fact that the theory is fundamentally non-probabilistic gives rise to the idea that all terms in the superposition are describing physical goings-on, and that will stop being true at the macroscopic level, so that we have, many worlds. And the emergent probability needs to be some story as to why, once we establish that the mod-squared amplitudes and their evolution over time have the right formal properties to be understood as probabilities, what more philosophical work needs to be done to, if any, to justify interpreting them as probabilities in that situation. But the point I want to get across is not here that the Everett interpretation is true, it's that the Everett interpretation is an attempt to make sense of quantum mechanics compatible with the way of decoherence. So, suppose we want to make sense of the physics that is done in doing early universe cosmology. What are our options? Well, one option is to adopt the Everett interpretation. I recommend this option. You can read more about it in this book, available from all good bookstores. It has some mild metaphysical ontological costs to pay, but they're not terribly serious. I shouldn't worry about them. Okay. You might not want to adopt the Everett interpretation. Maybe you're phobic about multiverses. Maybe you are relaxed about multiverses in principle, but you think there are ontological problems or that the probability problem is unsolvable or whatever. If you don't like the Everett interpretation, you could look for a non-Everettian approach to quantum mechanics that is compatible with the way of decoherence. I think in philosophy of physics, by the way, this is underexplored territory and deserves more attention. Possibilities. It is possible that certain ways of thinking about the relationist project fit this kind of story. My concern about this is that decoherence is largely a closed system project. It tends to be in the statistical mechanical framework where we take a completely isolated closed system of unitary dynamics and then we derive something about a subsystem, but we start with the closed system. So I'm not sure, but I think that's something that would be interesting to investigate from people who are more philosophically inclined towards the relational approach than I am. A lot of people in various bits of physics talk about consistent histories as a way of connecting to these ideas. Some of that turns up in technical work. Consistent history approaches tend, in my experience, either to collapse into not saying anything coherent or to collapse into the Everett interpretation, but that might be my failing, or it might just be that the right consistent history story hasn't been told yet. At any rate, the consistent history framework is very much, or at least important versions of it, are very much an attempt to make sense of the way of decoherence. So insofar as one can understand consistent histories projects as not being many worlds projects, then that would be an interesting way to go if one wanted to avoid the Everett route. There might be other possibilities. I like the Everett interpretation, but I'm entirely serious that I think it would be good work for philosophers to think about whether to what extent the way of decoherence is the Everett interpretation and to what extent there's room for manoeuvre between the two. Or, of course, we could reject the way of decoherence and find another way to do quantum cosmology. And we might be motivated to do so for one of two reasons. It might be that we don't think there's any direct scientific contribution to be made by getting rid of the way of decoherence and finding another way to do quantum cosmology, but that philosophical reasons make it essential. So I'm going to pause here to review briefly previous historical examples where we've modified scientific practice on philosophical grounds. Okay, I'm done. There's a more interesting reason one might want to reject the way of decoherence, and again, I think it speaks to work by some people in this room. It might be that we can actually get some scientific progress by bringing in modifications of quantum mechanics of various kinds, and sort of, if you like, take an end run around current work in early universe quantum cosmology. So attempts to use dynamical collapse theories, which are fundamentally non-unitary, to dissolve concerns about black hole information loss would be examples of this kind. Theory, the kind of Goldstein solution to the problem of time that comes from treating the dynamics of the Bohmian gravitational distribution as evolving in time, even while the quantum state is timeless, would be another example of this kind. That's not where my money would be, but certainly I think if just as a matter of the way science evolves, modifications of quantum mechanics are going to be successful in this kind of space, I think the way they're likely to be successful is not simply by trying to reproduce the predictions that can be made in extant quantum mechanics, but by seeing some way to leverage their distinct features, not just to solve the measurement problem, but to actually do some direct work in quantum cosmology. Okay, so let me wrap up. Why does cosmology matter to the measurement problem? It's not because we're doing the quantum mechanics of the whole universe. This is a line one often sees. A sort of classic, I think a little lazy argument for the Everett interpretation is alternatives to the Everett interpretation that don't involve modifying the formalism require an external observer. You can't be external to the universe. But it's been pointed out time and again, I think it's absolutely right, that we are hardly ever in cosmology actually modelling every degree of freedom of the universe. It's always possible in practice to say what we're doing is studying the long wavelength modes of some structure. So, digressing briefly, if you think about sort of inflaton models, there's a sense in which you want to say, look, I'm in a semi-classical regime. What I'm doing is I'm saying the system, that the complete quantum fields start in the Bunch-Davies vacuum and evolve forward. So, at least in principle, they're evolving everything. So I'm not completely convinced it's never, but in any case, I don't think this is a good objection. The real objection is just that what we're doing in cosmology is doing the quantum physics of a dynamically evolving system that's making contact with observation through its emergent macrodynamics, and not through anything that very straightforwardly fits the quantum measurement paradigm. I think that's true all over physics, actually, but cosmology brings it into particularly sharp relief. Thank you.
Excellent, right. We have actually plenty of time for discussion.
Thank you. So you gave some examples of types of scenarios which pose a problem for the way of the lab, or scenarios in which we seem to need to give a probabilistic interpretation towards square magnitude, even though there's many not obviously an observer performing a measurement. I guess maybe that those kinds of scenarios are also scenarios in which a number of approaches to interpreting Everettian probabilities are going to have trouble, like such things to do with self-limiting uncertainty or measures of existence affects our consciousness or decision theory even. So would you think that those kinds of scenarios also pose a problem, a specific problem for the Everettians in terms of probabilities?
Good, yeah, I think they pose a puzzle at any rate. So it's absolutely true that the paradigm examples of trying to make sense of the probability problem in Everett are kind of iterated scientific measure and check contexts. It gets particularly weird in anthropic contexts, but if we bracket those, there's still no one around to make bets of that kind. I think you could probably, because there's two thoughts. One is I think it's probably finessable. I mean, there's a finesse that goes something like, consider the observer who is sequentially being informed about bits of the distribution, and ask what's their appropriate betting strategy. So I suspect you can transform the problem of that kind. Over and above that, I mean, if you tell me the decision theory approaches completely fail, I'm certainly not going to give up the Everett interpretation. I think it's an interesting philosophical problem to make sense of probability in the Everett interpretation, but for philosophy of probability reasons, I don't think the problem is more severe than in other non-Everettian approaches. I think, by and large, what's going on in the foundations of probability in philosophy is you've got two things you have to do. One is you have to either find some fundamentally non-probabilistic thing that emergently has the formal properties of probability, like relative frequency or something, or else primitively posit that thing. And then secondly, justify why that thing that has the right formal properties of probability is probability. And I think the Everett interpretation does better than most at solving the first problem and better than most at solving the second problem. So if I thought the second problem solution just completely dissolved, I think, okay, it's a shame. I hoped we'd learned something about philosophy of probability here. Turns out we didn't. Turns out probability is just as much a problem for us as for everyone else. Too bad there are still many worlds.
Thanks. You briefly mentioned the possibility of finding other interpretations that would be compatible with what you call the way of coherence. And you also mentioned the relational, broadly speaking, relational strategy. Now, I'm sort of working on that, and so that's actually interesting. But then you also said that one problem that you anticipate there is that decoherence is, in some sense, is to do with closed systems in an important sense. That was just a little bit fast to me, and I was wondering whether you could elaborate on that.
Yeah, let me spell that out. So, because obviously in a certain sense, decoherence is paradigmatically about open systems. Closed systems obey unitary dynamics. What we want in decoherence is irreversible, stochastic dynamics. But if you look at the way we actually do decoherence, in pretty much all the cases I know, what we do is we start with a quantum mechanical description of the whole system we're considering, including its microscopic degrees of freedom or the external environment degrees of freedom. That whole system is treated as just evolving unitarily under some fixed Hamiltonian that we are assumed to know. Then we do stat math, and we say, okay, can we find, under appropriate assumptions, an autonomous dynamic sort of subsystem, which, when we can, is normally going to be highly non-unitary, is going to involve branching. But we're not, a fundamentally open systems approach would just posit non-unitary dynamics and take the fifth when asked why it had those dynamics. It's core to the decoherence project, and kind of core to non-equilibrium stat mech, and I think decoherence and non-equilibrium stat mech are very strongly overlapping on almost the same subject in quantum mechanics. It's very core to that project that one has ultimately a larger closed system with a unitary dynamics from which one derives the open system physics. So that's what I had in mind.
So I have a finger, and maybe it's a finger. I was a little bit surprised to see relationalism as listed in the way of decoherence. I can't really see how the way I understand it anyway, which may not be the right way, is it's perfectly naturally listed as one of the ways of the lab. So can you say, maybe I missed that, but can you say more about why
it's me speculating. I mean, relationism is not my baby, and I'm not particularly invested in it. I'm interested in it because I like attempts to solve the measurement problem that don't modify the formalism, because I'm part of I think that's probably something where quite philosophers can contribute. It's not obvious to me that the relational approach can't make sense of decoherence-based reasoning. It feels to me more naturally in the way of the lab framework, but you can take this, if you like, as an invitation to people who like relational approach, but are sympathetic also to my kind of argument that we use in the way of decoherence in early universe physics, to tell me how those can be reconciled. It's not, I don't have anything like a slam dunk argument that they can't be, and I think it's quite an important question.
Okay, good.
So, if I understand correctly, you have a generic posture that is more or less objecting to any attempt by philosophical considerations to be motivated to change physics. And I think you were going to give a few examples of what has happened historically where that didn't go well. Can you name, using, you can find some examples where it did go well, where it was a positive outcome for philosophical considerations to be taken into account? Progress in physics.
I mean, that was my joke, really. I can't think of any cases of that kind. Or to be more careful about it, there are cases where physics has run into internal crises of its own, and somewhat philosophical considerations have helped resolve that crisis. So Einstein's work on the relativity principle is a classic example of this. What I don't know examples of is cases where the methodology of physics is chugging along just fine, thanks. And where the methodology of physics is chugging along just fine, thanks. And somebody says, notwithstanding the fact that you've got a highly successful empirical practice here that's continuing to be effective, let's stop the train because there's a philosophical problem and go in a different direction. I mean, if I throw this in sort of Kuhnian terms, philosophical issues tend to be quite important in periods of revolutionary science. They don't tend to show up in periods of normal science. I mean, that's not an argument that it can't be done. It's a sociological suspicion that won't actually influence what people are doing.
So I have a finger on this as well. So I guess Newton would also not be a counterexample then in this case. Even though, of course, for Newton to establish the foundations of Newtonian physics, it was important to get sort of philosophically clear on the nature of space and time and motion.
Oh, yeah, no, absolutely. I mean, look, don't get me wrong. I don't want to say that getting philosophically clear on bits of physics can't be useful to physics. I don't want to put myself out of a job.
Right. And arguably physics at the time was not chugging along just fine.
Yeah, exactly. And it's also not to say that that getting philosophical clarity on what's going on in physics can't be informative to the direction of physics. I mean, again, I regard the Everett interpretation as part of trying to get philosophical clarity about what we're doing methodologically in applying quantum mechanics in, for instance, cosmology. What I'm somewhat skeptical about, and it's again, it's not really an argument, it's a historical observation, is situations where physics is proceeding successfully in domain or regime, and and we're not simply trying to clarify it, but we're trying to change its practice in a radical way. Now again, I mean, something like very early universe cosmology, where it's much harder to make empirical progress and where there are deep foundation questions, there is a place where that might not be so true. And the problem of time, for instance, is a deep foundation problem in an area of the subject which is not so kind of relaxedly connected to data.
So Bell would not be a counterexample either, so that, quantum mechanics was just, getting rid of all these early discussions about the foundation, philosophical discussions between Einstein and Bohr and these people, and then was chugging along just fine. But there was one guy thinking like, no, there's something wrong with the philosophical foundations, and then, Bell finds his theorem, and,
Bell is a nice example, but I don't think it works. And here's why I don't think it does. So Bell explored what was going on conceptually in quantum mechanics from a very hostile starting point. He succeeded in learning a hell of a lot about quantum mechanics and about the world by doing so. What he didn't succeed in doing is persuading physicists to stop shutting up and calculating. So again, that's independent of whether one thinks he should have succeeded. It's definitely true sociologically he did not succeed. And indeed, Bell, as everyone in foundations knows, the default interpretation by physicists of what Bell did is usually wildly wrong.
Daniel, did you have a follow-up on that?
Well, just a finger. So do you think we are in a situation in which physicists proceeding fine without...
Depends.
All being fine, you're happy with the way physics is proceeding?
Depends.
Do you see that dark spots in the horizon?
Depends on the area. I mean, I think the paradigm of doing early universe cosmology, where early means still in relatively close observational contact, so after the Great Quantum Wall, you could debate exactly where structure formation fits in. At the moment, I'd say that's continuing to be a practice that's data informed. It's possible, you can imagine a situation where it's hard to spot anomalies without hindsight. Maybe it'll turn out that dark matter, that there's a profound problem in identifying dark matter. Maybe the poverty of data we can get back to the inflation era will leave us with a persistent underdetermination problem in pinning down structure formation theories. These are all perfectly live possibilities. And right this minute, we're not at all sure how to do ultraviolet quantum gravity. And right this minute, we are deeply puzzled about the cosmological constant and the hierarchy problem.
And we are puzzled about the H0 problem, and we are puzzled about the non-observation of gravity, primordial gravity waves, and we are puzzled about the thermal inflation problem.
So you can. So you can't. Yeah. I mean, look, you can't tell in hindsight. So you can't tell, except in hindsight, which things are going to be puzzles that you'll eventually solve, and which things will, in hindsight, be the anomalies that led to theory breakdown. But look, I mean, let 1,000 flowers bloom. If you want to try to persuade physicists to change the practice of doing quantum cosmology on the grounds that they're doing it wrong philosophically, I mean, I wish you luck. I think you'll need it. But, actually, sorry, just one more thought. I don't actually think we're, just reflecting a minute, I don't actually think we're disagreeing. I mean, look, insofar as doing quantum mechanics completely differently turned out to solve the hierarchy problem, or turned out to solve the cosmological constant problem, or explain why we weren't observing primordial gravity waves, or halt inflation's progress, I don't think there would be any, do that thing and make a novel confirmed prediction, and I think physics will turn on a dime. That's exactly the kind of thing I was saying is the right way to apply a strategy of wanting to reject the way of decoherence and go in another direction. What I'm objecting to is, those are identifying physics problems and trying to modify our practice of quantum mechanics in a way that solves the physics problems. That, I think, is an extremely well-motivated project. And what I'm highly skeptical about is trying to modify physics practice on purely philosophical unhappiness with it. But the line, you could debate whether the line is sharp.
You distinguish between decoherence from small-scale effects and decoherence from environments. Then you, as quickly you said that somehow the small effects tend to be more important than the environmental effects. So does it actually mean that if there's such like a generic macroscopic state, you would really think it rather decoheres more because of its underlying small-scale degrees of freedom, so to speak, than through an outside measurement? So if you normally think of this cat interposition naively, then it should rather, in a very literal sense, self-measure rather than measure against the environment. Is this, so to speak, consequent? Do you have the question of at which scales, so to speak, one effect, the small-scale effect, so to speak, coherence becomes more important than the environment?
So when I said it was more important, I meant conceptually more important. I don't know which thing is the faster timescale in Schrödinger's cat. I mean, the thing to understand about a lot of these macroscopic calculations of decoherence is you shouldn't take the exact number that comes out so seriously. What these calculations always tell you is, given crude assumptions about the way in which the microscopic degrees of freedom interact with the macroscopic system, it will decohere ridiculously, blindingly fast. I mean, you get these timescales that basically say decoherence. These calculations will be made, and decoherence will sometimes happen faster than the Planck scale. Nobody literally thinks that's happening, but it's showing you that the timescale is essentially instant on the dynamical timescales of the setup. So I don't know which is faster there. The sense in which I think it's conceptually important is kind of quite closely linked to how you think about sort of irreversibility in thermodynamics. I mean, I think it's almost certainly the case in practice that if I want to understand why a system is equilibrating, then if the system happens to be set up in such a way that its own internal dynamics would be counter-thermodynamic, it's almost certainly the case that the gravitational influence of one molecule on Sirius is enough to break the effects there. And you can, and it's an honourable strategy, try to say, well, that is the foundation stone of irreversibility in thermodynamics. It's all about the external systems. But there's a probably more widespread tradition that says, well, while that's true, there's actually no essential need for the external system to doing that, because even the system in isolation is such that its macroscopic degrees of freedom will equilibrate or whatever. And I'm thinking in those kind of terms. So for Schrödinger's cat, absolutely, it is true that the external environment will measure the cat, but it's not actually conceptually required that it does, because if I place a cat in, whether a cat is dead is recorded in the cat's microbiota and in quintillions of little details in the body of the cat. And a cat re-interference experiment would require you to control all those degrees of freedom. And so decoherence of the is it alive or dead degree of freedom for the cat is going to be essentially instant and irreversible, even if the box the cat is in is somehow totally impervious to all interactions.
Maybe brief comment to what you said. So in quantum mechanics, there's often a situation which you recall the Vienna experiments by Zeiling and others. So they have one experiment where they always have the position of these buttons, the fullerenes and others. And one experiment in the cavity they introduce slow by slow external gas, and then you see gradients will re-emerge. In another experiment, they isolate but heat it up. So that the gradients come in a sense from the internal secreted, these are then escaping into the world. And so this is a different setup. You can have one influenced by one, the other one influenced by the internal environment. Of course, quantum cosmology is much more tricky, but at least in the lab you can study it.
I mean, there's an interesting feature of that example, which is, of course, it's the necessity of the thermal photon being emitted that makes the decoherence happen. And what's going on there, of course, is that this goes back to what I was saying about autonomy versus isolation. As long as we don't have thermal emission and it's just a closed system, then the centre of mass degree of freedom of the Buckminster fullerene decouples from the internal degrees of freedom. So while the internal degrees of freedom by themselves can measure whether the cat's alive or not, the internal degrees of freedom of the buckyball can't measure where the buckyball is. It needs to emit the photon to, I mean, you know this better than I do, but it took me a while to think this through. The centre of mass degrees of freedom do actually require something external to decohere them, whether it's an emission from the internal degrees of freedom or something else.
I'd like to return to the way of modification. And I agree that it seems unnecessary to have any modifications to understand the standard practice concerning the empirical base of cosmology so far. But as you also admitted, it might be a path towards new high-energy physics, perhaps. And I think that then suggests a very obvious strategy with which I think you would agree for anybody who would want to pursue the way of modification is to show precisely that there is going to be an interesting scientific difference and payoff really in, say, high energy quantum gravity that we could only reap if we were to go the way of modification, and that ideally would have some sort of empirical consequence, of course.
Yeah. No, I agree. I mean, the only thing I would say is the magnitude of the task is large. I mean, there's a lot of quantum field theory, and it makes a lot of good predictions at a lot of different places. And ultimately, it's a requirement of modification that it reproduces all that stuff. That said, I don't necessarily think it's a bad strategy. Instead of saying, let's try to modify, let's try to sequentially do a sort of bottom-up modification where we include, various versions of quantum field theory, to say instead, okay, from a top-down point of view, what can we say generically about theories of this kind? How would they look in a quantum gravity regime? What predictions? What predictions might they kind of make that would deviate from normal, like way of decoherence quantum mechanics predictions? I mean, how sympathetic you are to that is going to depend partly on whether you have those philosophical concerns about quantum mechanics that we were talking about earlier. I mean, if you're me and you think quantum mechanics itself is just fine facts, then you're going to probably think that the ask is quite heroic. If you think that anyway, at some point there will have to be a modification of quantum mechanics, it's just philosophically unacceptable, then you've got a very natural synergy, and you want to look for the place. You'd like to think in that case that the modifications eventually are going to prove their worth, and you're going to see them somewhere. I also find it really interesting that Bohm regarded, in his original work on de Broglie Bohm theory, Bohm regarded the fact that his theory was empirically equivalent to quantum mechanics as a defect of his theory, and he hoped that its generalization to the nuclear regime would lead to testable deviations between it. Of course, this is a period where quantum mechanics was kind of stalling on getting beyond QED and having a theory of the nuclear, so he was, sort of, in some sense, an early version of what we were talking about earlier. He was hoping that indeed the breakdown in the nuclear, the failure to extend quantum mechanics to the quantum field theory to the nuclear regime presaged a more general revolution, and that he was going to contribute to making that. I mean, that didn't work out then, but that doesn't mean that some similar thing couldn't work out later.
Yeah, my money wouldn't be on the way of modification, but I do think that's there's a sort of intrinsic scientific worth in having people with different philosophical predilections following, some of the different ways here.
Yeah, I think that's right up to a point. The only caution I give is that it's in relatively data-poor areas, it can be rather easy to come up with ideas and play with them, and the discipline of having to conform to, say, the full empirical predictions across QFT is quite a powerful one there. So I think I think the motivation of saying, because of the measurement problem and the bankruptcy of the Everett interpretation, some modification of quantum mechanics is in any case essential. Therefore, it makes sense to look in those directions. And we know quite a lot about the space of possible modifications, so let's use that to explore where we should go. That, I think, is motivated. I think I'd be much less... am I going to spend any time thinking, could we solve such and such problem in quantum gravity by developing an analytical collapse theory? Well, no, because I don't see any reason other than that particular reason to develop an analytical collapse theory, and there was like a million things you could try. But the synergy between the measurement problem, well, if you buy the Everett interpretation of the word, the synergy between the measurement problem and other problems of a physical nature in cosmology is a positive reason to do it.
Tim?
Thanks. This goes back again to the problems you pointed out for the sort of approaches that are broad-speed operationalists, or that I think you call it the way of the lab.
Yeah.
So you had these examples where basically you were giving examples of cases where we model what we think usually are objective processes in nature, and there's not really something like an operation or state or a measurement in the strict sense of that term. And I was wondering, if I try to put on my cubist hat, for instance, I was wondering how much I would be moved by that comment you made that interpreting, let's say, I think it was the rate of cancer in a certain population, interpreting that as a measurement was absurd. I mean, if you're a cubist and you think that a measurement is basically just anything an agent does to interact with the world in a way that allows you to extract information about it, something like that. And I definitely see, I'm struggling to put on a cubist hat, so I definitely see why there are reasons to be dissatisfied with this idea that was going on in the cases that you mentioned. But I'm wondering, is there a qualitatively new reason to be dissatisfied with the cubist story compared to the reasons we already have to be dissatisfied with that story in the context of a mundane, ordinary experiment?
Good. Yeah, good. So I think partly it's the continuation of the process over time, but mostly I think it's the theory-ladenness. So, what you've actually got in the cancer theory is a conjunction of various bits of nuclear physics, various, bits of political data on exactly, because some of the stuff is classified after all, exactly what was being done when, a whole bunch of what we've learned in lab and observational work about the effects of radiation on human tissue. You're putting, lots of these things are quantum and lots of these things are not quantum. You're putting these things together, and I think it'd be very hard to work out what the PAVM would be that would correspond to what's been done there. I mean, in a certain, again, make it sufficiently Procrustean, and I'm not saying it can't be done, but and in that sense, maybe it's only a quantitative development of the problem you made, but I think it's quite substantial. And you see to some extent, if you look at some of Fuchs's writing on this, he's more revisionary about physics than you might think sometimes. He's very happy to entertain the fact that dark matter is pointing to something fundamentally wrong. He thinks the whole of decoherence theory is bankrupt. And he doesn't comment on how to think about the experimental work on decoherence, but there's at least an issue there. That's just a side observation.
Yeah, I wonder if the same objection to the Procrusteanism of the scenario would not also apply to trying to rewrite it as like a problem if you wanted to interpret the quantum probability theoretically in this case. It still not also involve quite a strange and indirect rewriting of that problem.
I think I'll go back to my previous answer. I suppose this is a bit of a digression, but the way I would see the decision theory arguments is more of the form of arguments to the effect that mod squared amplitude and decoherent regime is probability, rather than necessarily things that are exhaustive of the content of the claim that it's probability. In other words, it needs to establish that it's probability, it needs to plug into our various inferential activities the way probability plugs into it. Extremely good evidence that's true would be being able to prove it's true in a certain admittedly slightly standard context. But there's the claim that multiple amplitude plugs into our scientific inferential proceedings the way probability is supposed to is somewhat broader than inside formalized betting contexts. One treats it that way. incidentally, I should have said in the other thing to your comment, I mean, I'm sort of slightly carefully avoiding operationalism as a label for way of the lab. This is the reason for my neologism here. I mean, I don't think Bohrian complementarity, Copenhagen-style interpretations are well characterized as operational. They have an attitude to the quantum formalism that's slightly difficult to make sense of, but they have an ontology, just classical, and the quantum theory is informative about that ontology. Whereas something like Heisenberg is just flat out operational, and the cubists are close to it. But you can adopt that way of thinking without committing to operations.
All right, so please join me in thanking David once again.